Okay, well, we're going to go ahead and start the session. The title of this session is called SQL to NQL, Structured Querying for JSON. My name is Kevin Holder, and I'm the Vice President of our Technical Field Operations here at Couchbase. And I'm honored to be joined by my colleague, Keshav Murthy, who's a Senior Director of Engineering here at Couchbase, who's responsible for the NQL language. From an agenda perspective, I'm going to cover a couple of foundational topics relatively quickly, and then I'm going to hand it off to Keshav, who's going to drill down into the NQL language. But I am going to talk about the SQL language just a bit, even though most of you probably are familiar and probably know SQL in depth. I do want to talk about it because it is the foundation for NQL. I'm also going to talk about JSON and some data modeling concepts at a very high level because those tie into NQL as well. And the reason why it's important to go through these foundational concepts is because NQL is developed on that foundation, right? NQL is not just an afterthought that we've added to our product just to try to give a better, easier syntax for getting at data. NQL fundamentally was built on a solid foundation. It is pure SQL with extensions to support JSON data. So I'm going to hit those foundations very quickly, talk about some of the limitations using key value without a query language like NQL, and then I'm going to hand it over to Keshav to drill into the language itself. So first of all, no discussion of SQL can really start without recognizing the early days, right? Back in the 90s, late 80s, early 90s, Oracle really took off, became popular, and that's what really kind of brought SQL into the mainstream. So you guys will all recognize the guy on the right side of the screen there, Mr. Larry Ellison. You guys may not recognize the guy on the left. This is Don Chamberlain. And Don actually invented and helped design the SQL language back in the early 1970s, right? So way before Oracle was ever around, Don was working on defining SQL at IBM, actually. And we've been fortunate as a company to have Don actually as an advisor to us and to our engineering and products teams as we've developed the NQL language. So very kind of cool to have the guy that created the initial language now working with us as we create the language that will now take this paradigm forward. So SQL, this is just a quick and dirty Wikipedia definition. Structured query language, it's a special purpose programming language designed for managing data held traditionally in relational database management systems, but today we're going to talk about how it's now being used through NQL for NoSQL databases as well. Originally based on relational algebra, and it consists of a data definition language, data manipulation language, and a data control language. Some of the core features of SQL, first of all, it's obviously based on the relational model, right, from the very beginnings. It is a declarative language. Statements such as select, update, delete, insert, merge. It also supports arithmetic, logical, and set operators. And then a whole host of data types, right? These are some of the more basic ones: numeric, character, date, time, etc. SQL is not just used for selecting and querying data, it's also used for schema design and management as well. The popularity of SQL really had a huge impact on the development of business applications, right? So as Oracle started to gain popularity back in the 90s, people started to learn SQL. It really allowed developers to develop business applications much more rapidly than they ever could before. And that became kind of a snowball effect, right? We were able to leverage skill sets now because there was a common language. We could leverage them across applications, across organizations, et cetera, et cetera. So the impact was huge. And some of the things that the database vendors began to put into their databases in order to support SQL and kind of facilitate more effective application development were things like ACID transactions, right? So two-phase commit type scenarios, I can now do that using SQL and the database engine, and that's so much easier than trying to code that manually the way that we had to before, right? The coding for that can be very, very complex. SQL was enriched to include things like stored procedures, right? Let me take a SQL statement and wrap that as a procedure that I can then call from all points of my application or even from multiple applications. Triggers were added, right? Let me take a SQL statement and let me attach that statement to a table, and then anytime that table is mutated, that SQL statement will execute, right? A very elegant way to kind of do things as data is being updated in the system. Also things like views, indexes, catalogs were added, optimizers were added to make the queries perform better. We saw fourth generation languages emerge that really helped drive the popularity of SQL as well. So 4GL languages such as Oracle Forms allowed developers to rapidly develop applications, and it was using SQL on the back end to communicate with the database. So again, it just helped solidify SQL becoming a standard. And then we've seen expansions and integrations supporting things like spatial data, text data, JSON, and message queues as well. So it continues to evolve. So now that we have the SQL foundation there, let me talk a little bit about JSON, right? And what we're really trying to do, not just with Couchbase and with JSON, with NoSQL, it's really with any database system that we implement. What we're really trying to do is model what we see and experience in the real world, right? So in the real world, our website may have customers, and that customer will have a name and a date of birth and billing information, credit card information, connections, et cetera. And so what we need is an effective way to model that so that we can capture that information, store it in our database, right? And so there's kind of 4 properties that I want to kind of touch on in this section and compare and contrast how these properties manifest themselves in the relational model versus NoSQL. One is a rich structure, right? We've got to be able to support a rich structure that includes detailed information about our customers, multiple credit cards, for example, multiple purchases, a long purchase history. So a rich structure needs to be there to do that. Relationships to other data needs to be supported as well. And then the value of the data will change over time, right? We know over time the customer information will get updated. Perhaps this Jane Smith gets married, she changes her name, she adds a new credit card, she has more purchases, so the information will be updated over time. And then the structure will be updated over time as well, right? So as we start to learn more about our customers, we may have additional information that we need to track, which will cause us to change the structure of our data. So modeling that in the relational world looks kind of like this, right? I've got 5 tables here, a table for each of those main subject areas that I want to track. And then I've got foreign keys that link those together, right? So from a structure perspective, I can capture that rich structure, certainly with a relational model. I can normalize it. I can then use join queries to pull that back together. I can handle the relationships that I talked about through the joins and then through database constraints. Values, as data change, I can use my insert, update, delete statements to update that. And then the structure, as the structure changes, I can use the alter table statement to change the structure of my tables. This is where things start to become a little problematic with the relational model though, right? If I alter a table, that results in I have to bring the database down, I have to reconfigure the database, I have to update the data, the application needs to come down, I have to perhaps migrate the application to a new version control, et cetera, et cetera, et cetera. So those are some of the downsides to being able to modify the structure of your database with the relational model. Not that NoSQL solves all of those, but certainly it makes it much, much easier. And some of those issues are why the NoSQL space kind of evolved in the beginning, right? We wanted more schema flexibility. We wanted an easier way to manage change, both in the business requirements that may be changing, as well as in the structure of the data, right? Because we know that change is inevitable, right? The business changes, the information about our customers change, the information about our products change, so change is inevitable. So we wanted a more effective way to manage that change than what we had before. And then JSON comes onto the scene, right? So JSON is a text-based format that's used to represent object data. And in Couchbase, we store our data as JSON documents inside of our database with a key value structure, right? So your key might be your customer ID, then your value would be a JSON document that contains their information. So all the major data types are supported with JSON, number, strings, booleans, objects, arrays, nulls, etc. And the nice thing about JSON is it's hierarchical, right? I can have nested information inside of my JSON documents, and I'll drill into that a little bit more here. So if we go back to kind of our real world customer example, what this might look like in a table format would be a customer ID column. In this one it's CBL 2015. a name field called Jane Smith, and a date of birth. In the JSON NoSQL world, I would actually take that customer ID, and that would actually become my key to do a lookup against the NoSQL database. And then I have some flexibility on how I can model the data, right? The top example shows a very simple representation of the name, just as a string, Jane Smith, whereas the bottom one, we've broken the name down into a couple of different attributes called first name and last name, and I can reference those accordingly. So we have a little more flexibility with JSON and how we can structure those objects. So the rich structure that we talked about needing to maintain, I can easily do that with JSON as well, right? If I want to add billing information to that document that we created on the previous slide, I simply add a new key value pair, add one for billing. I create an array where I can store multiple credit cards, and I'm good to go, right? I can change this at the application layer. It will update my documents, and I don't have to go through the process of reconfiguring my database, bringing the application down, so on and so forth. Value evolution, right? If I want to update the data, very simple. Key value set, no problem. I can update the data easily with this model. If I want to change the structure, this is one key advantage. I can simply continue to add new key value pairs to my JSON document over time. If I start to track new information about a customer, I can simply add that as a new key value pair inside the JSON document, and there's very, very little impact to the application layer. I can also have relationships inside of these documents, right? So you can make decisions on how much you want to keep in a single document versus splitting things out, right? If I have a customer document, I may also have customer loyalty information. I may not want to embed that all in one giant document. I may want to put that in a separate document and then have a key that maintains that relationship. So those are the types of decisions that you can make. So this just kind of compares and contrasts that customer object in both models, right? So, again, in the relational model, I've got 5 tables. I've got joins to pull the information together. So every time I access the data, I have to hit 5 tables, join it together. The database does this. It assembles a result set, returns it back. Every time I save the data, the database will disassemble it, put it into the proper tables, et cetera. Whereas on the JSON NoSQL side, I have my document key, and then I have my document that contains all my information. So very efficient to read and write that entire customer record with a single shot. So this table just kind of summarizes the pros and cons of both, right, for those 4 properties that we were looking at. So the rich structure, relational can handle the structure. Downside, as I just mentioned, is the constant assembly and disassembly. JSON can handle it, and there's no assembly required. The relationships, I can represent those relationships in both. I can query those in SQL with the relational model. Traditionally, this was a downside to NoSQL, but now with NQL, we've addressed that concern. So I can query my relationships. Value evolution, obviously both can be easily updated. And then structure, this is really another area where NoSQL, I think, wins the day, right? On the relational side, it's a little more uniform and rigid, a little more manual to change, requires downtime, whereas with JSON, flexibility and the ability to dynamically change my data model. So now that we've talked about SQL and JSON, let me quickly kind of cover a few considerations, as you're thinking about, what would a SQL language that actually could handle JSON need to consider, right? So again, if we touch on why NoSQL to begin with, it's all about agility, scalability, performance, and availability, right? And we also know in the real world as developers that business use cases are really what drive our applications, right? So, we get requests such as, process this order at checkout, generate a list of shipments that are due today, load my new inventory data, merge customer lists together, right? These are all things that can be represented in SQL statements to help drive our applications. In the relational world, I can take those use cases, craft a SQL statement, submit that to the database, it does the processing and the work, it returns a result set back to me, right? Key point there is the database engine is doing the work for me in that example. On the NoSQL side of things, this is where traditionally NoSQL systems kind of run into a bit of a snag, right? Until NQL. So typically, data is accessed through key value APIs with NoSQL systems, right? So you're scripting things through APIs. You have a limited query language. And so at Couchbase, we said, we need a richer query language in order to address this gap. And really the gap is this, right? Let's take my customer example again, right? And let's say I've modeled it such that I've got customer information, I've got orders in a separate document, and I've got loyalty information in a separate document as well. With the key value model, my application needs to get the customer and then go get their loyalty information, then go get their order information, and then kind of massage that together for something that can be displayed on the front end, right? So the application is handling the logic of putting those things together. That's okay for simple use cases, but if you take an example like this, right? Let me find high-value customers with orders greater than 10,000. Now I'm looping over millions of rows. I get the orders back. I total those orders up. I grab additional information. The code for I mean, if you just kind of think and let this marinate for a minute in your mind, the code for this becomes very, very complex, right? Very hard to maintain. And that's where a language like Nickel really gives you the best of both worlds, right? With Couchbase, I can do my key value for high performance scenarios, but for scenarios like this, I have Nickel to make me much more productive and much more effective. And the processing is happening on the database engine side as opposed to in the client code side. So why SQL for NoSQL? It's kind of like this, right? You could buy a BMW without a steering wheel, but it's kind of hard to steer, right? So Nickel gives you the steering wheel to help you navigate more effectively. And so the considerations for a SQL language that will deal and handle JSON data, I can't just rely on a static schema anymore, right? The schema is flexible, so my SQL language needs to be able to handle that as well. I need to be able to handle nested objects, nest and unnest data within that JSON structure. I need to be able to work with a distributed data store, right? In NoSQL, my data is distributed horizontally across a cluster. I need to be able to work with that and then optimize performance around that. So those are the considerations that we took into account when developing Nickel on that SQL foundation to support the JSON model. A lot of industry work has been going on in this space for a while. The databases now support JSON. All the major databases. Microsoft is doing it. UC San Diego SQL++ project, which is the foundation for our analytics offering, is doing some really cool stuff there. And then obviously Couchbase with our Nickel language we feel is the most robust version out there. So with that, I'm going to hand it over to Keshav Murthy, Senior Director of Engineering, who's going to talk more about Nickel. Thank you.
Okay. Thank you, Kevin, for the motivation and the introduction to Nickel and SQL. In the next 20 minutes, I'll try to cover as much as the Nickel overview. The rest of the details are in this book. If you haven't gotten the book already, you can stop by in our expo booth. If they run out, just send us a note or leave your address. We'll make sure you get every gory detail about Nickel from this book. So, as what is Nickel, right? As Kevin said earlier, SQL is a declarative query language. SQL engines take sets of relations as input and give you the results set as a relation, right? It's a relational data processing engine. What is Nickel? Nickel takes sets of JSON as input, processes it depending on your query, and gives you back a set of JSON as a result. It's a JSON in, JSON out. There are other query processing engines which process JSON or other semi-structured data, but gives you back flat data out. Here in Nickel, the whole design is you don't lose any information, you don't lose any flexibility in processing JSON, right? Whether it's nested structure, arrays of objects, objects of objects, it's JSON in, JSON out. So let's look at a simple example. You have the JSON structure on the left-hand side, and you want to issue a query like select customer.name, address.zip, phone, the first phone. The reference to the name, it's a simple scalar value here. Address is an object. You are able to use dotted expressions to address specific fields within an object. If you have arrays, you can address every element of an array within your in your projection. From class looks like your standard SQL, and in the where clause, again, you are able to address a scalar value within the address object, address.zip. And the second predicate, in this case, if the status is an array, you are able to have a predicate on an array to say, I want only the customers in this zip code have a premium status. They could have multiple status depending on your schema design. So I want to make sure this customer has a status called premium. And I want premium customers who have purchased something. That means JSON by nature is flexible. There is no, you don't create a table or a JSON schema before you start inserting. So not only the values in relational schema, you can have a valued attribute or a nullable attribute, right? You can have actual values or nulls. In JSON, you could have valued attributes, null attribute, as well as things can go missing, right? So you can query the JSON in Nickel to say, okay, I want only the customers who have done some purchase, right? This is an example of the flexibility in the query language. Of course, this is an example of select statement. I'll show you the example of insert, update, delete, merge. It's a full-fledged query language. In that sense, Nickel is designed so that you can develop interactive applications on Couchbase, full-fledged interactive applications, and also bring both the SQL skills and SQL based applications onto Couchbase, right? So at a technical level, Nickel's goal is to give developers and enterprises an expressive, powerful, and a complete declarative query language for querying, transforming, and manipulating JSON data, right? Okay, let's dig into the details of how this is done. So you saw a simple query earlier. This is a little bit more complex query. At the high level, right? What is SQL? SQL does select, join, project, right? Selection happens based on your where clause. Join is based on the joins in your from clause, and projection is in your projection. There are a few more clauses, group by, order by, and all that. They are all, but at the outset, it is select, join, project. What does Nickel do? Nickel does select, join, project, but because of the complex structure of JSON, we have added two more additional operators: select, join, nest, unnest, to handle arrays or arrays of objects, and then project. So you can see not only we are inspired from SQL, we have taken all the good things from SQL and we have extended SQL to operate on JSON. So let's see what are the extensions. We talked about the objects. Let's assume name is an object. You can have dotted expressions, right? Customers.name.lastname. This can go on forever, as long as you have your nested structure. So the dotted expressions help you to reference values within the objects or the objects themselves. Okay, and projection looks and feels like SQL. It is, and you can have scalar expressions or aggregate expressions in your projection list. In the from clause, you have from orders unnest line items. So unnest, if you have an array, you want to flatten the array so that you can do relational like processing. Unnest helps you to do that. And in this case, orders have list of line item, array of line items. I have flattened the line items to give it a name called order line. That order line is valid in the context of this query. And then once you unnest, I want to find, I'm interested in the customer information. I'm joining the orders with customers. Here, I use the join clause, and by default, we support inner joins as well as left outer joins. By default, it is inner join. I'm joining orders with customers on customer.orders.customer ID. So the joins in Nickel have to have a parent-child relationship. That means I'm joining the customer IDs to the primary key of the document key of the customers. In Couchbase, as you know, every document in a bucket has to have a unique document key. It roughly correlates to the primary key of a relational table, and this uniqueness constraint is enforced in your inserts, so we know it's unique. So in terms of the joins, you can join any two key spaces or any two buckets if you have a relationship either from the parent to child or child to the parent. And then group by looks, feels, and works just like SQL, and the post aggregation, you can have predicates on the aggregate with the having clause, and order by on any of the items that you have projected, right? So as you can see, this looks and feels close to SQL, but it is extended to work on complex structures, arrays on JSON. Here is the insert clause, insert into customer values. The first argument is the document key, and then the second argument is a JSON document, right? So, and you can have a simple single JSON document, or you can have full-fledged, you can have an array insert with multiple documents with a single insert. Update, again, looks and feels like a standard SQL, except any place where you can have a reference, you can have a complex expression. You're updating state here, you can have updated address.zip or whatever. Just like SQL, Nickel is composable as well. You can have subqueries anytime, anywhere an expression is allowed, whether it's in the from clause or in the projection list. And standard ordering and pagination is supported as well with limit and offset. You saw the examples of joins already. Subqueries are supported, non-correlated and correlated subqueries, as well as aggregation, min, max, count, average. And here is another extension. Because you can return arrays from a projection list, sometimes, in a simple scalar values, you want to have simple aggregation, sum, max, sum, average, min, max, etc. Sometimes you want to, if you have hobbies, for example, that you want to return a list of hobbies, you can have an array aggregate which can combine the hobbies of your customers and return it as an array. So we have extended aggregates to include an array aggregate. Standard set operations, union, all, intersect, except, works just like the standard SQL. The underneath Couchbase is a distributed key value store. We have performance optimization in terms of if you, in your application context, if you do know the document key, instead of using an index to find the document that you're interested in, you can simply use keys and give the document key and fetch the document directly. You can give one keys or multiple keys, or you can have a subquery to generate the list of keys. It's in the performance optimization. It's ideal for a hash distributed store because we know where the documents exist. We can fetch directly from there. For joins, we support inner and left outer joins. We right now implement nested loop joins, and joins are executed from left to right as you have specified in your query. We don't do the join ordering yet, join reordering yet. You saw the example of unnest. Unnest flattens the array into the higher level object, so you can do the grouping, aggregations, and so forth. And nest does the opposite of it. If you have multiple elements in multiple documents, you can create an array and insert that array into a separate object, or you can project that as well. So unnest and nest are complementary to each other. So join, nest, and unnest can be chained in any combination, and you can have any number of joins, nest, and unnest in your from clause. Once you have arrays and arrays of objects, you need a lot of expressions both in the predicate as well as in the projection to manipulate and construct these arrays and collections. We have a very rich set of expressions that helps you to enable it. JSON provides flexibility. JSON provides objects, nested structure, and so forth. But one of the key difference between a standard relational model and a JSON model is arrays. Arrays gives you maximum flexibility. If you create an array, you don't care whether a customer has one hobby or a million hobbies, right? And you only pay for the number of hobbies they have. If the array happens to be 3 elements, you store elements with three arrays, arrays with 3 elements. If they have a million hobbies, you just have a longer array. You're paying only for the number of elements in there. You don't pay in advance. But you do need to understand when you manipulate arrays, when you project arrays, when you aggregate on arrays, you have to have you have to understand both how the schema is structured as well and write the appropriate expressions to manipulate them and create the right indexes to manipulate the arrays. So the understanding JSON model and implementing it efficiently depends on your understanding of the actual JSON implementation as well as understanding arrays. So for this, for ranging over collections, the any expression will give you the predicate expression to find out if an array has a particular value. Same thing with every evaluates the arrays to find out if every element within the array satisfies a particular predicate expression. And you can have a mapping of multiple values within an array for an expression using the array expression, and within gives you the ability to traverse through the array to find out if any element within that substructure satisfies your predicate. And you can construct these JSON literals and arrays dynamically, and you can traverse them as well. In terms of JSON data types, we have numbers, strings, booleans, arrays, booleans and null, and arrays and objects. And the moment you have arrays and objects, you can nest. Arrays can have objects, can have arrays. Objects can have arrays of objects. You can mix and match. That is what at the core gives you the flexibility that comes from JSON. Okay. So we also have introduced missing because you want to interrogate missing. We have the support for encoded binary values as well. The important type that is missing from JSON is the date, timestamp, and datetime. You can store that as ISO 8901 strings, and we have a rich set of functions which manipulate this datetime strings. One thing that you do have to remember is in JSON you get flexibility. With flexibility comes responsibility. That means the JSON, if you reference a non-existing column, you don't get any error. In relational, if you refer to a non-existing column, you get a column not found. Here, there is no column not found. There is no type mismatches. The JSON is case sensitive, so you have to use the right key names in your queries. So otherwise, you'll get the missing value. That your query will not fail, but you don't get the data that you want. We looked at some examples of insert, update, delete. We have the full-fledged support for it, including merge. The key thing to remember is JSON is a distributed NoSQL data store. That means our atomicity is at per document level. We don't have multi-statement transaction. Yeah, here's an example, and like I said, not just any insert. Anywhere an expression is allowed, you can construct a JSON literal, and it's a standard key value JSON literal. There are only 3 things that are important in databases: performance, performance, performance. So without a good indexing, no query language is going to perform very well. So we have full-fledged support for not only many types of indexing. Indexing is high performant and very flexible as well. You can create index, drop index. Explain helps you understand the query plan that we have chosen, what index is chosen, what plan is chosen. That helps you to optimize as well. I'll be talking about indexing and explain in the next session in the same room. So here's a simple example of index. It looks and feels like a standard index that you create in a relational system, except you can index nested fields, arrays, and so forth, right? Here are the varieties of indexes. You can create primary indexes. Primary indexes are roughly equivalent to your table scans. It's great to have them during your development. In production environment, if you don't expect ad hoc queries and don't want people to be doing primary scan, basically table scan your application, you don't have to have them in production, so that's one less risk for you. Yeah, we support simple indexes, composite indexes, functional indexes. For example, when you want to do case-insensitive searches, you can simply uppercase, lowercase the values in the index and give the right predicate, so functional index. Array indexing, I'll be covering that in the next session. Array indexing gives you the ability to index individual elements of an array. Array can be pretty complex, 1 level, 2 level, we handle that. Partial index, when you have a very large data set, you want to create indexes on parts of the data. So we had a customer who just was interested in the last 1 month worth of data. They're only going to query last month worth of data, so you can create index only for that. Covering index is a performance optimization, and duplicate indexes gives you HA. Okay, let me quickly cover what's the, you all know the Couchbase. I won't go through the Couchbase clustering, except to say Couchbase, you can run multiple services, but for the production environment, you should run one service per node. How does Nickel query execute? Applications give query over REST API. Query service does the parsing semantic analysis and creates the plan. Sends, if it chooses the index or two to evaluate the query, it sends scan request to the index, gets the results back, and then it goes to the data service, gets the results back, does the post-processing, and goes back. Just one point is the data that is streamed back from the index service, when the data is getting streamed back from the index service, we automatically and immediately go to the data service. So the index processing and the data processing is happening in parallel. It's not a stop and run method. So this is inside the query node, what happens. So this is a kind of internal architectural view of things. When you see those stages where there are multiple blocks, we can parallelize those things. The scans, the fetches, the joins can be parallelized as needed. There is a max parallelism parameter that you can control. By default, it's 1, but the data fetch is always in parallel. We have a great ecosystem with Simba, CData, providing JDBC, ODBC drivers, and multiple customers, multiple partners providing us both BI, ETL tools. In summary, Kevin talked about the example of finding customers with orders more than 10,000. Writing an application to do all this processing and maintaining it is expensive. So writing a declarative language and let the query engine take care of the complexity of execution is makes your developer productivity improve. Okay. In summary, if you know SQL, how does it map to Couchbase Nickel? Database is a bucket. Table is mapped to bucket. In the Nickel, the subset of the bucket we refer to as key space. Row is a JSON document. Column is a key value attribute pair. Index is an index. SQL supports SQL data types. We support JSON data type. Joins, SQL has a richer join methods with full outer join, left outer join. We have inner and left outer join. Full outer and right outer can be rewritten as inner and left outer. Primary key in SQL is document keyness. In terms of actual statements, the left and the right looks very close, and that's by design, right? We have a saying in our R&D saying that we don't want to change anything from SQL if there is no need to. If there is no need to extend the concept, there is no need to introduce a new syntax, right? So we stay very close to SQL. As Kevin mentioned, Don Chamberlain works closely with us, so we make sure we adhere to SQL, and it's good for business, good for everybody. And more similarities with the prepared statement, execute, grant, revoke, that's going to come in 5.0, as well as explain. Explains a query in both cases. Okay, this is the last slide, right? In summary, right, in terms of the statements, we have similar statements. With terms of query operations, we have similar them. Yes, there are some cases where traditional systems have richer query, but we are catching up pretty quickly. And with Nickel, you can have schema over JSON. And finally, I mean, this is the core point, right? What Nickel does is gives you the ability to do set-based processing, query processing on JSON. Okay. Thank you very much. Yeah, we'll be around between the sessions, after the sessions, if you have any questions. Thank you.